Welcome to my YouTube channel. In this video, we are going to present another method of calculating the magnetic field at any point around a current carrying conductor. Now, we are still going to be using the Bell-Savart law, which is given by this expression here. Now, we assume a conductor carrying a current I, and it has a distance of 2x. From here to here is x, from here to here is x. This side is negative x and this side is a positive x. The distance from this point to this point is a, and we are interested in determining the magnetic field at this point. The distance from this point to this point is the vector r, and the contribution of the magnetic field as a result of this small element is given by this expression. Okay, from this expression we have our sine theta. Theta is coming from this theta. Our dx is also known as the s, given by this expression, because this is the x-axis, this is the y-axis. Also, we have our r. We can represent our r in terms of a and theta. So r is equal to a all over sine theta. That's opposite all over hypotenuse. So we have this expression. Then we can also represent our x in terms of theta and a. So it means that opposite all over adjacent. So we now have x equal to a all over time. That the reason why we have this negative sign is because this side is a negative part of x and this side is a positive part of x. So now that we have all these expressions, we now substitute them into this original equation and we move. Okay, so first thing is to differentiate this particular x with respect to theta, because there is the x in the previous equation. So by the time you differentiate this one, you get this expression, and the step goes thus: a all over tan theta is the same thing as cos theta all over sine theta. So using v du minus u dv all over v squared, we have this expression, where if you keep your v, which is sine theta, you differentiate this, you get this. If you keep your u, which is cos theta, you differentiate this downward, you get this, all over v squared. If you factorize your minus out, it will cancel this one, and sine square theta plus cos square theta will give you 1. So you end up having this expression. And 1 all over sine theta is cosec. So because we have squared, it becomes this expression. Now you now substitute the value of the x, the value of r, into the original equation, and you get these parts. When you now integrate both sides, it will result to this expression. If you simplify, you cancel out and it will result to sine theta. You integrate this side, it gives you b. This expression is a constant, so you take it to this point and integrate from theta 1 to theta 2, where theta 1 is the angle, this theta 1, and theta 2 is this angle, theta 2. In our previous video, we gave reason why it must always be theta 1, this point and this point. We said the point, the angle that it leaves, the current leaves behind, is the theta you must consider. Okay, so when you integrate this one, you have cos theta. After cos theta, you substitute your values, the upper and lower limits, and you have this one. So this is the general formula that can be used to solve all problems relating to a straight line or a straight current carrying conductor. So it is called the general formula. Let's see how do we use this formula. Now let's consider a problem of this form. We have a length of a conductor, 5 meters, and we are interested in calculating the magnetic field at this point x. Now the first thing you must do is join the two edges to that point. So if I trace this edge, it forms a straight line which is perpendicular. If I trace this one to that point, it must. So whenever you have a problem, always trace this edge and this edge to the point. So if the point is here, you trace it this point and this one. If the point is here, you trace this one to that edge and trace this one to that edge. Hope that's okay. So once you do that, the next thing is to calculate. Check the arrow of the direction of the flow of current. It's going this way.
So the current will leave this angle behind, and it will also leave this one behind. So this one will now be our theta 1, this one will be our theta 2. At the end of the day, once we know the value of theta 1 and theta 2, we'll substitute them inside here. Okay, so let's see. Our theta 1 is 90 degrees, no doubt about that. Now, to get our theta 2, we must know this angle. And to know this angle, we'll use opposite all over adjacent, which is tan phi. We call this angle phi. Tan phi is equal to 2 all over 5. And phi is equal to arctan of 2 over 5, which is 21.8. So this angle will now be 180 minus 21.8. So therefore, theta 2 is equal to 158.2. Okay, so we substitute the values into this expression. Take note, our A is 2, which is the length of the length in the previous diagram. Then cos 90 is 0. This particular one is this. Then by the time you simplify and take care of, you get B equal to this expression. So our magnetic field at that point is given by this expression. We are leaving these 2, but if this value is known and this value is known, you can substitute and you put the units. I hope this helps.
Please share and subscribe to my channel.
Thank you.